Welcome to the next lecture of the subject digital signal processing, and we will be discussing multi-rate signal processing in this lecture. What is the meaning of multi-rate signal processing? If I have any digital system, it operates at certain rate, the rate at which the bits are being transmitted. The transmission of bit from any analog signal is a byproduct of processes such as sampling, quantization and encoding. So, rate is determined by the sampling process. So, if I have an analog signal, I convert it into a discrete signal. So, not analog signal, a continuous time signal is converted into a discrete time signal using what is called sampling, and in sampling the rate is determined. At what rate, bits per second or samples per second, we are actually sending the signals. But if there is a digital processor and a system constituting several blocks of subsystems, it is possible that each subsystem actually operates at different frequencies, and therefore it becomes important that the processing takes place in different frequencies to cope up with varying demands of each subsystems. So, different system functions operate sometimes at different rates. The rates are also related to bandwidth, because we know that the bit rate is related to bandwidth. So, if bandwidth consumption of a certain part of the subsystem is to be reduced, it requires to reduce the bit rate of the system. The bit rate is directly proportional to the sampling frequency. So, in overall system, it is possible to process different subsystems at different rates. The rate is basically determined by the sampling rate of the system. It can be varied using some time varying functions, and that gives us to the need of multi-rate processing. So, suppose I have so for example, there are 3 blocks which are connected of any system. All of them are operating at different frequencies. So, suppose it is operating at a frequency of fs1, this is operating at fs2, and this is operating at fs of 3, and all of them are different. So, what is our requirement? First of all, if there is an analog signal, it needs to be converted into a digital system signal, that is by sampling. That sampling will be to the frequency fs1. But in multi-rate processing, we want to change the frequency in between the system. This is a complete system comprising of 3 blocks. So, we will change the frequency here. So, we will make it fs2. fs2 can be larger than fs1 or smaller than fs1, that is a different thing. But we want to change fs1 to fs2, and we also want to change fs2 to fs3. So, multiple rates are required within a given system. That is the complexity that is desired from a system. There are 2 ways in which this can be achieved. The first way, the first stage is resampling and reconstruction. That is that if I have an analog signal, I will sample it. I will have the samples here. I will join the samples, and I will again sample it at the desired frequency to obtain fs2. So, we resample it and reconstruct it. Basically, reconstruction the construction is taking place first, and then the sampling part. So, that is possible. That is what we will see firstly, because in theory that is the basic concept. Secondly, what we can do, we can change the sampling rate all in the discrete domain. That is more efficient, of course, because we do not want every time to reconstruct. When you are reconstructing, you are coming back to the analog domain. So, if it can be avoided, it should be avoided, and that is the case that in most cases the sampling rate conversion takes place in discrete time. To study further, it is important that we look at what is the sampling theorem. Sampling theorem is a thing that is a very important theorem, but it takes into considerations few assumptions. The first and basic assumption is that there is a continuous time signal which is band limited, which means there is no frequency component beyond a given b hertz, and suppose which is not possible because no signal can be bounded in frequency. For that, the time varying signal, the inverse Fourier transform has to be infinite duration, and it is not possible to obtain infinite duration. Therefore, is the first assumption that the signal is band limited to B hertz. If it is so, it is possible to reconstruct from the samples obtained of the signal, if the samples are obtained at sampling frequency which is greater than 2 times of the maximum frequency content of the signal. The maximum frequency content of the signal, if it exceeds the maximum frequency content of the signal, the sampling frequency, the number of samples per second that we will take, it is possible that we can reconstruct the signal faithfully. In other words, the reciprocal of sampling frequency is sampling period, so Ts should be smaller than 1 by 2p. What happens in this process is that if I have any signal and I want to sample it, I actually multiply the analog signal, the continuous time signal, with a train of impulses. Since impulses exist only at particular instances, it's an impulse signal. So each impulse will get multiplied to the continuous time signal, and the product will only exist at particular time instants. So we will get the sample values, we'll get the sample values. What happens in the frequency domain? So if I have the signal to be a band limited signal, we are assuming that beyond B hertz the spectrum of the signal does not exist, and this of course is the Fourier transform of the continuous time signal. If I take the product, actually the Fourier transform of train of impulses is also a train of impulses, so I have omitted that. But if you take the samples, so Fourier transform of this last plot will be something like this, that multiple copies of the same signal will be created in frequency domain. And of course, our intention is reconstruction. Our intention is never for sampling. The sampling process definition is incomplete without reconstruction. So what is reconstruction? Is getting the original spectrum back. How will I get the original spectrum back? Is by taking and filtering out the center portion. We will use a low pass filter having a cutoff frequency of B or more hertz, but more also getting the guard band into the consideration, so that the middle spectrum, that is the original spectrum, can be retrieved. Now this process of reconstruction by joining the samples in time domain is called interpolation. So the low pass can be reconstructed by the signal xt only if the sample signal has the component xt by ts. We will see how this happens. Actually what happens is that if I have the multiple copies, this is the sampled signal, this is the sampled signal. So if I have the sampled signal like this, I can obtain the middle portion by filtering it out through a filter g of f. These both are actually manifestation in frequency domain. So if I multiply x of f with g of f, I get suppose y of f. This is the reconstructed signal. This is the reconstructed signal. The reconstructed signal. So the reconstructed signal is basically product of the sampled spectrum and the spectrum of the low pass filter. If in time domain it is, if in frequency domain it is multiplication, we know by properties of Fourier transform, in time domain it is simply the convolution. Now if g of f is of this form, it is basically a rectangular function having a cutoff frequency suppose up to fx, minus fx by 2 to plus fx by 2, isn't it, by direct definition. And the inverse of a rectangular function is a sinc function. A sinc is sin pi x by pi x. So I have just g of t, which is the inverse of the filter, means the impulse response of the filter. This is the frequency response of the filter. So the impulse response of the filter g t, small g of t, is sin pi t by tx by pi t by tx. So what happens actually is, if we are taking the product in frequency domain, it manifests to convolution in time domain. Now what is GT? GT is a sink. So if I calculate the convolution, you can understand in convolution we have sum and we multiply the signals and its shifted version, and the product is added. So in this case, if the signaling instants are defined, then it is possible that maxima of each sync pulse will give you the value of sampled signal, and all the other signaling instants of that sync pulse will be 0. Similarly, the maxima of the second sync pulse will give you the value of the second sample that was picked, and all the other values of the second sync pulse will be 0 at signaling instants. So you can understand, in this manner I can frame the samples and I can join the samples with freehand to reconstruct the signal. This is what is happening in frequency domain also. The spectrum which is at the middle is the original spectrum. We multiply by the low pass filter, we get that back. But what happens in the interpolation is that we compute the convolution, and that convolution gives me the reconstructed version of signal. So that can be written very easily as the convolution sum in this case will be y of t will give me n minus infinity to plus infinity x and tx and gt minus ntx. If we compute the summation in n, we will end up getting a function in t. Please understand that this is sample, very important point. So we are representing it in continuous time, but we are computing the summation as convolution because it actually is a sample. So it is some sort of y of nts, isn't it? It is some sort of y of nts. So it can be understood that this is the computation, and the computation is such that the signal is multiplied by sync and its shifted versions. So if I want to change the signaling rate, what I can do, I can take y of t which is defined as x and ts into g of t n minus tx, and I will take a sampling instant mty. So I will get what is y of mty. Now this ty is the new sampling period, and that is by replacing this t by mty in this expression. Now if we look at this, if tx is equal to ty, these both are equal, so it basically becomes m minus n into anything tx. So then this is a simple convolution, it becomes a simple convolution. But when it is not equal, when ty is not equal to tx, then what happens? Then I can frame by taking tx common from that relationship, and I can frame mty by tx as something which is km and delta suffix m, which this we have taken from Procase itself, where km is the largest integer greater than or equal to the mty by tx. This is basically km, which means that this is the integer value. In simple terms, it is the integer value, and this is the fraction times. So ty by tx, if it is an integer, delta m will be 0. Other than that, it is some portion of the integer and the other remaining fraction values. If I put in place of mty by tx this value, I will have basically km plus delta m minus n, the y of mty. Now we are just rephrasing it so as to understand what is the relationship. So if I can again write this, my y of mty is summation n starting from minus infinity to plus infinity x of ntx g of tx km plus delta m minus n. In this case, you can understand it is a kind of a convolution. I am saying kind of a convolution because it is actually in t, but we are breaking down it into samples. In this case, this is fixed. Understand that if it is x of k and h of n minus k, and summation is in k, is commutative. which means I can also write it as at x of n minus k and h of k, isn't it? So in this case, it is the first case, A. So this is A, because we are keeping the signal there and we are shifting the filter through which it is passing. The ideal filter is sync. And in the other case, what we can do, we can change the variable n by using this substitution, k is equal to km minus n. So my limits changes from minus infinity to plus infinity. In place of n, I can write k minus k, and in place of km plus this n can be replaced by km minus k. So I basically have k plus delta m tx. The summation is in k, so please remember the variable k is here only. So here what we are changing? We are changing the input, which means this is the B case. We are changing the B. So two ways of interpreting the same results is either I shift the input and multiply by the fixed filter or filter impulse response, or I keep the input constant and multiply by the shifted versions of the filter. Also, since it is not only KTX and there is something other also remains here, it is generally time varying. And also the system is linear but time varying. It is not time invariant, it is a time varying system. Okay. And if mty by tx is equal to km plus delta m, this implies that mty is equal to tx km plus delta m. So which means that what we are writing, y of mty can also be written as tx multiplied by km plus delta m. So our basic result becomes like this, and this is very important, that y of tx multiplied by km plus delta m. Remember, this is by how much we are changing the sampling rate, multi-rate processing, है ना? So tx multiplied by km plus delta m is equal to x of km minus k into tx, the last slide it was there, and g of ktx plus delta m tx. The km variable provides the requirement for input sample, which means how much shift is to be done in the input sample is represented by km. What is km? Is the integer value. The integer value of mty by tx. Remember, the integer value of mty by tx is basically km. Other terms, delta m, which is the fractional value, determines the impulse response coefficient. So what is the change in the impulse response that is required? So if I represent this in linear systems, it is basically transmitting the original sampled signal through a filter having a impulse response of this g n tx plus delta m tx. Tx is common basically, and this is a discrete time linear time varying process, as it requires different impulse response for each output sample, isn't it? If the impulse response is same for a given input, then we say the system is time invariant. But the system is time variant because if x and tx changes, the delta m changes, and therefore we require a different filter. So it is a time varying filter, a time varying system, and we get a system which is now operating at a frequency fy, which is equal to 1 by ty. It was originally operating at fx, capital F of x. What does this also imply? That if we look at the interpretation of this, is that if I have an analog signal, so this blue line is the analog signal, this is an analog signal. This analog signal was earlier sampled using tx. So the sampling instants were these. The sampling instants were like this is kmth instant, this is km plus 1, this is km minus 1 into tx. So these are the earlier sample values. The values are these, isn't it? The earlier values are these. The crosses are the previous sample values, but we want to change it. We want to change it into ty. So the interval changes. The interval is ty. The interval is ty. Earlier the interval was tx. It changes. The period of taking the samples changes. It is multiple rate, and that is a multiple of delta m's, and m. So add delta m plus m ty, m plus 1 ty. So in this manner we can obtain. So these blue points are the samples which are now taking. It is evident from the plot कि crosses which were taken earlier were more samples compared to dots which are less samples, but basically the intent is that we can change the rate at which the signal is processed by using this fundamental equation. Now, this equation has two very simple scenarios. We'll just quickly look at them. The first one is decimation, which is down converter. In this case, we basically have fx by fy is equal to d, which means ty is equal to d times of tx. So, in that equation, we can just substitute ty by tx at d. In the previous equation, we just put ty by tx is equal to capital D. Capital D is the decimation. So, how it happens? Decimation is generally represented by capital D and an arrow of downwards. So, suppose we perform decimation for an example by 2. So, if I have samples and this is actually representing n is equal to 0 points. So, if I have xn is equal to, it starts from minus infinity, the values of n are -2, -1, 0, 1, 2, 3, 4. In this way, we have basically samples of original signal. I want to decimate it by 2. So, decimation by 2 means I want to make the sampling rate half, which means that I will discard one sample between 2, which means from 2 I will take 1. This is decimation by 2. From between 2 I will take 1. So, which means between 3 and 6 I will discard 4, between 6 and 4 I will discard 2, between 4 and 1 I will discard 9. So, you can see when decimation takes place, the new signal I of n is having samples less than the original samples, but sampling rate has changed. So, this is what can be done in discrete domain. Now, what is the effect of this? So, suppose I have xn, this was my original spectrum. I know that x of z, the z transform is represented by n minus infinity to plus infinity xn z raised to the power minus n. If I represent the above signal like this, this will be, it starts and then this is n minus 2. So, this will be 3z square, 4z, 6z 0, 2z inverse and so on and so forth. What happened to y of n? Y of n was this. So, we discarded few samples. So, if I framed the z transform of this comes out to be 3z plus 6 plus 4z inverse plus z minus 2, because 9, 2 and 4 have been eliminated. So, z transform is like that. Now, is there any possibility that we can connect the two? Is there any relationship between capital X of z and capital Y of z? Yes, there is. So, capital X of z is this, Y of z is this. So, what will be capital X of minus z? You can understand, in capital X of minus z, the even parts will keep their signs, the odd parts, the signs will change, the odd powers, the sign will change. What happens when we add them? Since these negative signs will cancel out, we will have only the even orders. But what is the relationship between this and this? What is the relationship between these two? Very evident that first of all, I also require that the powers are half. So, this 3z square should be 3z, 4z minus 2 will be minus 1, 4z minus 4 should become z minus 2. So, basically all the powers should also be half and can be added and divided by 2 because they are coming twice. So, y of z can be taken from capital X of z by using this relationship for d is equal to 2. For d is equal to 2, this can be done. So, y of z is capital X computed at z 1 by 2 and capital X of minus z raised to the power 1 by 2 and 1 by 2. What is the frequency response? We basically put z is equal to e raised to the power j omega, isn't it? That is the relationship. I put that in this above relationship. So, I have e raised to the power j omega by 2 minus e raised to the power j omega by 2. Now, what is e raised to the power minus j omega by 2? This minus sign I can also compute by e raised to the power minus j pi, isn't it? Minus j pi means what? Minus j pi means it is minus 1 because this is cos of pi minus j sine of pi. Sine of pi is 0. So, it is cos of pi which is minus 1. So, I can minus pi. Then I can take this common. I can write it omega by 2 minus pi. I can also rephrase it there is by 2 also. So it is capital X j omega by 2 plus capital X j omega minus 2 pi by 2, isn't it? So y of the new frequency response is related to the previous frequency response like this. So if I look at it very importantly, this is having a period of, understand that capital X of e j omega has a period of 2 pi. So if it has a period of 2 pi, if the independent variable is divided by something, the period gets multiplied by it. So it has a period of 4 pi. This also has a period of 4 pi, and therefore this Fourier transform that we are getting y of j omega is required to be a period of 2 pi. Which means what? That there is a periodicity of 4 pi. So from 0 to 4 pi is there, and the y of j omega should be between 0 to pi. So it is evident that some parts are being lost in frequency domain. This is also the case in time domain. We have dropped some samples. So it is evident in decimation we lose upon information. So suppose if just for an illustration purpose I have drawn this, that if there is capital X of e j omega like this, if I take omega by 2, the spectrum will basically flatten out, the period will become 2 times, and means the period will become from 2 pi to 4 pi. And if I draw the second the shifted version, capital X of j omega minus 2 pi by 2, it will be something like this, the third portion, and the original spectrum is basically addition and division by 2. So we will have a spectrum which I am just following right now. This will be the output spectrum. So basically what happens, that there is aliasing, isn't it? The frequency components of B and C are actually merging in case of the last, and therefore there is some sort of aliasing for which a filter is generally used before decimation is done. That filter has a cutoff frequency of pi by d, just to ensure that there is no aliasing. If in general we take this decimation process, then by if by an order m we do it, the new signal is called x of mn, and the frequency, the z transform can be written as e raised to the power j 2 pi k by m and z raised to the power 1 by m. Earlier it was z raised to the power 1 by 2 for a case of m2. So this is like this, and the spectrum can be again given as 1 by m and capital X of omega minus 2 by k by m and whole summation from k is equal to 0 to m minus 1. So this will be the case when m is general. There is also a second method which is called interpolation. In interpolation we up convert. So in up conversion we basically show it by an arrow and L, and which means that we now have a signal x of n by L. Understand this, that this has to be an integer. So n by L has to be an integer, isn't it? So if n by L is to be integer, you can clearly understand that if it is not so, then it will be 0. So it will be, that discrete time signal will only exist when the time instants are integer values. So n by L has to be integer value. So if n is equal to 0, nothing. If n is equal to 1, L has to be 1. If n is equal to 2 and L is equal to an integer, so the values of n that will be permissible will be even. That is very concludable. If n by, so suppose if I take a case of upsampling by 2, so x of n by 2 we are doing. What happens in n by 2? We actually are multiply the time axis by 2, which means if this is at n is equal to 0, since it is 2, which means I am between 2 samples I am putting one more. I am just multiplying everything by 2, the time axis, which means the 0 will become 0, the 1 will become the minus 1 will become minus 2, the 1 will become 2. This is the time indices I am talking about, which means that in between we will insert zeros. So upsampling means that we insert zeros between 2 consecutive samples. So in this case it is for n is equal to 2. Very easily the Z transform, if we look at this, the Z transform for this from decimation perspective also we have seen, it is 3z square plus 4z, because the power of this will be z raised to the power positive, then 6z 0, 2z inverse, 4z minus 2, 9z minus 3, and in this manner we will go. So, y of n is basically with a 0. So, what happens? Each and every point the power of z is doubled, isn't it? Since it is 0, it does not change. The 1 changes to 2, the 2 changes to 4, and so what is the relation between the two? Very straightforward. Capital Y of z can be obtained from capital X of z by placing z is equal to 2. And in this case, if I just change to frequency domain, again z is equal to e raised to the power j omega, and therefore we will have e raised to the power j 2 omega. Now understand this also. If the period of capital X of omega is 2 pi, then for 2 omega this period will become pi. So, it will contract, not expand. In this case of up conversion, the frequency response will contract. If it compresses, it is possible to only draw the compressed version, but actually this has to be periodic in 2 pi. This is periodic in pi, but this has to be periodic in 2 pi. That has to be considered while plotting the spectrum of the signal. So, which means to say that if I have some spectrum like this, which is from minus pi to plus pi, this is the spectrum of x e j omega I am talking. So, this can be compressed downwards using up conversion. The spectrum will converge. So, basically what I am saying is that a spectrum will converge from minus pi by 4 to plus pi by 4. But if I am drawing from this perspective, it still needs to be periodic, and this shall repeat always. This shall repeat. So, if I am plotting capital Y of j omega, it should repeat. It should be at 0 and at multiples. So, the periodicity of capital Y of j omega should be kept in track while plotting the spectrum for interpolation. So, these are the two things that two processes that are involved for converting the sampling rate of the systems. So, that is all from my side. Thank you.